Good morning, everyone. Welcome to a very special Power Hour edition of Electro-Matic's Tech on Tap educational webinar series. The title of today's webinar is called Make Your Machine as Safe as a Fortress. And what we're going to be talking about today is machine safety lifecycle, from the risk assessment process all the way into the safety implementation process of that machine. Got a couple of speakers for you today. First of all, myself. My name is Matt Klein. I am an automation specialist for Electro-Matic products. I work out of our West Michigan office. My primary focus at Electro-Matic is working with Siemens factory automation and digital connectivity and power, as well as Fortress Interlocks products. I am an ANSI B11 licensed machinery safety specialist, and I've been in the industry for about over 20 years, working with Siemens, among other products like Rockwell, Schneider, and Mitsubishi, in my previous life as a controls engineer. My counterpart, George Levinoff, is also going to be presenting today. George is also an automation specialist, but also a technical team lead and works out of our Ohio office. He's responsible for the same products that I am from the Siemens side of things, and is also an ANSI B11 licensed machinery safety specialist. He's got a couple more years experience than I do. We've taken very similar career trajectories. You could almost say we're professional twins. I wouldn't say twins in the traditional sense. I'd say it's more like that movie with Arnold Schwarzenegger and Danny DeVito back in the 80s and 90s, where George got all the height, he got all the good looks, and got all the brains. So
yeah, you could definitely tell by our pictures that we are not twins.
Definitely. So let's get started here. Couple of housekeeping tips. If you could please make sure that your microphones are muted during the presentation. We'll be going through some slides here as well as a live demo. If you do have any questions, you can please put those questions in the chat function of Teams. George is going to be monitoring the questions, and if we have some time at the end of the presentation, we're going to go ahead and address those. If we run out of time, what we'll do is we'll do our best to answer those questions individually. So let's just start out by talking about safety. Well, what is safety? If you look online at the Merriam-Webster website, the very first definition of safety is the condition of being safe from undergoing or causing hurt, injury, or loss. So that's really specifically what we're talking about when it comes to the automation world and equipment here. And you may ask yourself, well, why is that important? Well, it's very important. And we've got some statistics here from the National Safety Council data. Every 7 seconds, a person is injured while on the job. That counts up to a lot of injuries every year. 14 of those injuries every day are fatal injuries. So it's very important in the workplace that we keep our people safe. And a side benefit of keeping those people safe is loss of production time. With those workplace injuries that occur every year, over $104 million of production days are lost annually due to those injuries, to the tune of over $160 billion. So our primary concern, obviously, let's keep our people safe. But if we're keeping our people safe, we're also making more money. So there's a couple of good benefits of making sure that our machines are safe. So looking at a piece of equipment, how is it that we make this machine safe? Well, it really starts and ends with a risk assessment. So there's an entire risk assessment process that you can run through that's very well documented to make your machine safe. So you may ask yourself, well, this sounds like a lot of work. I don't really want to do these. Do I have to do this? Well, the answer is a resounding yes. Whether you're building equipment in the US, whether you're building it overseas, whether you're shipping it in the US or shipping it overseas, there are standards in every region of the world that require you to perform a risk assessment. In the US, the ANSI B11 standard is a very specific standard that talks specifically about the implementation of a risk assessment and putting in risk reduction measures to make sure that your equipment is safe. And we are going to talk, actually we'll be referencing that standard quite often while in the presentation here. As far as performing a risk assessment, there are different parties that are definitely responsible for performing a risk assessment. The end user primarily is responsible for their portion of their risk assessment, as well as the machine supplier. And in an ideal world, when you're coming up with a concept of that machine, you will be collaborating between the supplier and the end user. And you can also see the entire product lifecycle of that machine is always involving a risk assessment. So that risk assessment is kind of a living and breathing document that's going to follow that machine from the conceptual design all the way to the decommissioning process of that. So what we'd like to see is users and suppliers collaborating. If they can't collaborate, they better be communicating with one another with the findings of their risk assessments. So as you're performing a risk assessment, whether you're a supplier, a user, or collaborating together, you definitely have to involve qualified personnel. Ideally, you've got design engineers, you've got management, you've got machine operators, and you have maintenance personnel that are all getting together, communicating with one another, figuring out how to make that machine safe. You also definitely have to utilize the regulations and standards for the specific country or region that you're sending that equipment to. Collaboration and communication are key to make sure that the risk is identified and make sure that you're telling, if you're a supplier, you're telling that user what is the residual risk on that machine. So communication is definitely key. There is a specific process for performing this risk assessment. It's a multi-step. It involves, first of all, preparing and setting the limits of the assessment. And really what this comes down to is figuring out what you're doing the assessment on, bringing together the right team of people is key on this, and then moving right into identifying hazards and tasks that are associated with that machine. I have an operator that's loading parts. That's a task. I have a pinch point. That's a hazard. You need to identify all of the tasks and the hazards associated with that piece of equipment. Once you've identified those tasks and hazards, you can then assess what the risk is. What is going to happen here if someone can get hurt? The next is to implement a risk reduction measure. So I want to reduce the risk on that. Once I've reduced that risk, I can then reassess what is my residual risk. So as long as your residual risk is an acceptable level, at that point, you can validate and document your risk assessment. So what you need to do is do this for every single task and hazard that is associated with that piece of equipment. And obviously, if you've reduced the risk and assessed that and it's not acceptable, you better go back to the drawing board and figure out how to make it acceptable. What we're going to be concentrating primarily in the next couple minutes is these 3 steps. So we're going to identify, assess, and reduce. And let's start with the identification process. We've got this sample machine here. And what this machine is an extruded aluminum cutoff machine. And we've pulled our team together. You'll see the people that are on the team a little bit later when I show you the example risk assessment document. But what we've determined are 4 primary hazards associated with this piece of equipment. We've got a couple of hazards associated with the saw here. We've got chips that can come flying off of the part. Obviously, there's a cutting hazard with the saw itself. We got a couple of clamps here that are clamping the part down. That'd be a crushing hazard. And then our transport rollers can be a crushing hazard or a pinch point. So we've identified those tasks. Now what we want to do is assess the initial risk. So many of you may or may not have seen this particular flow chart for achieving functional safety. This is not a flow chart you're going to want to use for assessing the risk. So once you have done your risk reduction measures, you would use this flow chart to determine what safety level your control system needs to be at in order to meet that risk reduction level. When we're actually doing the initial risk assessment or assessing the residual risk, the risk involved in the task is a function of the severity of harm that can occur and the probability of occurrence for that harm. So there are several different risk scoring systems that you can utilize. One of them in particular is table 2 inside of the ANSI B11.0 spec. And what it does is it defines the severity of harm from minor all the way up to catastrophic. And it does get into specifics on what is considered minor, what is considered moderate, et cetera, et cetera. And next, you look at the probability of occurrence. So from remote all the way up to very likely. So as you can see, as the severity increases and the probability increases, obviously your risk level will also increase. So it can go from high to negligible. This isn't the only risk scoring system that's available. there are a couple as well in Annex F of the ANSI B11 standard. So now we've assessed the risks. We know what our risk levels are. Now we want to reduce them. Well, how do we do that? How do we determine that? What you can use here in ANSI B11 is the hazard control hierarchy. And this defines classifications for the different risk reduction measures that you can take to make your machine safe. It goes from the most preferred all the way down to the least preferred. And obviously the most preferred is inherently safe by design. What you want to do is you want to take those risks, design them right out of the system if you can. If you can't design them out of the system, at that point you can implement engineering controls. And that has to do with guarding the system, putting in a safety PLC or safety relay, and safety type of devices. And finally, you have administrative controls. This is training your people, making them aware that there are risks there. If we look at those three different categories, let's take a look at a couple of examples. We've got a window washing team here. They're hanging from the top of a building. Obviously, there's some risk involved there with falling. What we've done in the inherently safe by design category is actually given these guys extension units so they can wash those windows without hanging onto the building. They can be standing at the bottom here. Some examples of engineering controls. We've got safety guarding. We've got solenoid operated interlock switches. We've got two-hand controls. We've got mechanical trap key systems as well. These are all engineering controls that you can implement to reduce those risks. And finally, we've got administrative controls. I've got beacons. They can tell me when there's a fault in the system. I've got signage on my machine saying, okay, there's a pinch point here. Keep out of this area. Hazardous voltage here. Lockout tagout is an example of an administrative control. And finally, we've got PPE. So making sure your people have the right equipment so that when they're operating that machine, they won't get injured. Let's jump right back to our cutoff machine. We've got our team. We've identified the hazards. We've assessed the risks. Now we figured out how we're going to reduce those risks. And we're going to do that two different ways. Well, actually three. Inherently safe by design, what we're going to do is we're going to change the mechanical design of this thing so that these clamp plates and the transport conveyor are actually implemented in the machine frame. So the operator is not going to have access to those at all. So inherently safe by design, we've actually taken that risk out of the system. The other thing that we've done with engineering controls is we're going to install some machine guarding with a polycarbonate front on it to eliminate chips flying out at the operator. And the final thing we're going to do is we're going to put a door with a solenoid operated interlock switch on here so that we can open up the guarding, we can clean the saw, we can change out the cutting wheel. But we're also going to take that to another level where we're only going to allow authorized personnel to do it. So at that point, we can assess the residual risk. And what you might see for some documentation is going to be this example risk assessment. So we've got our robot units, extruded aluminum cutoff machine, gives a description of the risk assessment. This is the team that we've assembled to help us determine what that risk is. You can see myself and George are on there. We've got some other folks from Electro-Matic and some of our vendors here. Our sources we're listing, these are the standards that we're going to use. Obviously, we've got our Power Hour webinar here, pretty informative. We're going to use that as a source as well. And here we've identified the tasks and the user responsible for it, what the hazard is, the assessment. So how dangerous is it? How likely is it to occur? And here we've assigned our risk level. So we go from medium to high here. We document our risk reduction measures. We've assess those residual risks, and we determine that by making those changes to the system, they're either negligible or very low. And also we've got some responsible people here, whether the task is complete, who is responsible for it, and then whether it's in process or not. At that point, you validate your solution, which George is going to touch on in a little bit, and then providing your documentation. The next part of the presentation really has to do with implementing the safety related part of that system. So we determine what in our risk reduction measures that we're going to install this guarding. We are going to put in a PLC. We're going to do some other risk reduction things. So with that, I'm going to turn it over to George. He's going to talk more about the engineering controls.
Great, thanks. Thanks, Matt. Yeah, so like Matt said, we're going to now talk a little bit about how we would implement some of these engineering controls and what the pieces parts of it would mean. So next slide. Yep. So here we're going to talk about the safety related part of the control system. So when we talk about this system, it's basically broken down into 3 different categories. We have our detection category. This is all of my input devices. So these are going to be things like push buttons, limit switches, door interlocks, anything that's going to be a detection device inputting into my system. Then I have my evaluation component. The evaluation component is essentially the brain. This is making the logical decisions based on what it's detecting to decide how we should react to the detection, which finally then is the reaction portion. So these are essentially my outputs. So what are we doing? Are we turning something on? Are we turning something off? Or how are we handling whatever we're detecting? That's what happens in the reaction portion. Next. So a couple of examples of detection devices. So upper left, real simple, hardwired emergency stop button. This would be wired into a fail-safe input on a PLC or perhaps a safety relay, something like that. Point there is it's a hardwired device. Then just below it, we've taken a hardwired device and we've networked it. So that's an example of a Profinet push button station that is fail-safe communications back to a safety PLC. This also just shows additionally, there's a ribbon cable that shows some standard push buttons that can also be added to it. Then finally, we have our door interlock system. And this could be as simple as monitoring a door, that a door is open or closed, or we could lock a door based on certain conditions. We can also potentially add some additional IO to whatever this device is. And all of these devices can either be hardwired back to either our safety system, whether it be a safety relay, safety PLC, doesn't really matter, or we can be networked back to that PLC. Next. Then we have our evaluation system. So this could be from the very simple safety relay. Maybe you have a very simple system. So all you have is an emergency stop button that is driving a main contactor for the main drive. This is really simple. There's not very many changes that are going to happen in my system. So safety relay could be perfectly appropriate. Maybe we start adding some features. So we want to add a programmable safety relay. Maybe our system is becoming more complex. We've got doors that open. We've got some wind down time on our machine. Maybe we know we're going to be making changes. We have local e-stops, global e-stops. Things are starting to get more complex. So maybe we want to introduce a safety controller into the system. Could be anywhere from a basic controller like the S7-1200F up through the S7-1500F, including the protected or washdown PLC, or perhaps even a fail-safe software controller. So essentially a PC running the safety software on there. Next. Then finally, we have our output devices. So this is what we're driving. It could be anywhere from a safety contactor, could be solid state, could be a drive, like those 2 examples there show a G120 AC to AC drive, or the S120 common DC bus. Both of those examples could either be hardwired to the terminal strip on the front of the drive, or we could network it back to our safety PLC and do everything over the network. Okay. Okay, so that was just kind of a little bit of an overview there. So let's just talk for a second about what does Electro-Matic have that would fill in some of these gaps. Now, we're going to kind of restrict ourselves to the components that we're going to show during the live demo. So next. Okay, so what do we have for guarding solutions? So from Electro-Matic, we have a system called robot units. Robot units is a very simple system to assemble. It is extruded aluminum, so you cut them to length. So technically, we could use our example from our machine of doing the risk assessment. That was cutting extruded aluminum. Cut your pieces to length. A couple of the highlights here that we like about this is it's easy for one person to install. One tool necessary. So what that means is that all the fasteners in the robot units line use the exact same Allen screw. So whether you're using the example that's shown here or there's wider versions, that slot is always the same size and use all the same tools. So we can use mesh guarding, we can use polycarbonate guarding. There's lots of different options. And again, we're restricting ourselves just for what this demo is going to be, but we could do a lot more with robot units than just build fencing. Next. Then we've got Fortress Interlocks. And again, I'm going to restrict myself to just the AmGuard Pro product line. There's a lot of other switches that Fortress Interlocks provides, but this is the one we narrowed in on because this is the one we're going to show you during the live demo. So, and it could be anywhere as simple as a just knowing is a guard open or closed. We could lock a guard shut. And one of the benefits here is the retention force of that lock is really high. It's 10,000 newtons. So this is going to prohibit somebody from opening a door that we don't want opened. Then we can start adding these little pods onto the AmGuard Pro. If I want to add an e-stop button, reset button, request to enter, different options that I can add. And of course, everything can be hardwired back to either a PLC or a safety relay or what have you, or it can be networked back to my safety PLC, either over Profinet or Ethernet IP. Okay. And then finally, my last component here is our safety PLC. So here we've chosen the S7-1200F as our safety PLC of choice. And a couple of the features that we like about this is number one, the safety PLC does double duty. So the standard automation code that you would typically use to run your machine goes in this PLC, plus the fail-safe code that you'll be adding to do any of the safety functions. All inside the same unit, nothing extra to buy. Additionally, any code that I write in an S7-1200 is easily transportable into an S7-1500. When I say easily transportable, literally copy paste between the two PLCs. There's no migration, no conversion, you just copy paste it. And finally, one of the other things we like about this is this uses TIA portal. So the TIA portal is our automation system moving forward, programming all of the Siemens devices. So if you've used TIA portal to program a standard PLC, you already know how to program a safety PLC. The functions and everything, the look and feel is exactly the same. Okay. So now at this point, we would want to, we've reduced all our risks, and now we need to validate our solution. So now we need to go back and make sure, did we do our job correctly? Okay. So a couple of different tools that are out there that we can use. One of them is the safety evaluation tool, which is a part of the TIA selection tool. So the TIA selection tool is the tool that we use for choosing components in the Siemens world, but I can additionally not only select the components, I can also go back and I can do a safety evaluation. And this is my check. I need to make sure that I did the right job, that I implement things properly. Am I getting the times that I need? How does everything work out? This is the documentation at the end. Okay. All right. So that was kind of that. Now I'm going to turn it back over to Matt, and Matt's going to step us through a live demo of configuring some of this stuff.
Appreciate it, George. Like George said, what we're going to do is implement an actual safety solution from the programming side of things using, if you see on the screen here, this is the Siemens TIA portal software. And this is where we're actually going to program our safety PLC to perform the risk reduction measures that we determined in our risk assessment. So before I do that, what I want to do is switch over to my camera view. So let me just stop sharing. And then, George, do you see my camera? See the station here?
Yeah, we sure do. But if David, if you could turn off of your video, because we're split between you and David.
Okay. Well, I'm just going to explain this while David is doing that. This is the system that we're implementing. So a couple of the components in here, you can see we've got our S7-1200 PLC. This is our safety controller. We've got a Profinet push button station. This implements both safety e-stop as well as some standard I/O. We've got our Fortress Interlocks solenoid operated gate unit. This is a power to unlock device. So it will actually remain locked. You cannot open the door unless power is applied to the solenoid. And we also have our robot units fencing and guarding. We've got a door here. This is going to simulate access to the saw area of the system. We've got safety contactors that are running our conveyor system. And if you remember, we've inherently designed the hazards out of our safety system. So we don't necessarily have to turn off our conveyor. if we want to access our gate. And then finally, we've got a green light here that's behind this door. This is going to simulate running our saw. So when we turn our saw on, we're going to see this light come on. Just a couple of things real quick about the equipment. This is that fastener that George talked about with the robot units. Makes this stuff really, really easy to put together and assemble. It fits into these slots here. You turn it and it locks itself in. They're all spring loaded, so they're not going to fall around. This makes it very easy to screw them in and very easy to assemble these. Also with the robot units, we have actually an RFID device here where we can read an employee badge and determine whether or not we want to access the system. And that's exactly what we're going to do here with some of the badges that I have shown on the table. Just another thing I want to point out about the AM Guard Pro units. These things are extremely customizable, so you can kind of fit them to every application. You can see with this one, we've got the guard unit. We've got some push buttons and lights on it. This is all a single unit. The reason this product is so great, or one of the reasons, is that you can actually fully customize this. If I wanted to separate the control station and then hardwire this into this control station to send everything back via Profinet, I could do that just by using the two plugs at the bottom of this. So pretty great system, pretty flexible to use. With that, I'm going to switch it back to looking at my portal software. So let me share that screen. Okay. So we do have kind of a limited amount of time here. So there are a couple of functions that I'm going to do in my program that are going to be some pre-configured things like typing in tag names and things like that. And what I'm going to do is utilize the library functionality of the TI portal in order to make this process a little bit faster. The library functionality in Portal is a very powerful tool. If you're creating your own user standards within your company, you can definitely utilize this to come up with your own standard programming blocks. What I've done already, just to kind of move things along, I've already inserted a PLC into my project. So this is my 1215 PLC. If I double click on this, I can configure the individual elements of the PLC. So if I look at a safety rated PLC, in the properties, there are a couple of safety rated parameters. So this fail safe section, I can actually enable and disable the safety function of the PLC. Disabling that, I just use it as a standard PLC. If I enable safety, then I can implement the safety functionality. Under protection and security, this is where I can assign password protection for the hardware of my system when it comes to the safety, as well as your non-safe access. At this time, I've chosen not to add password protection, just so I don't have to type in that password every time. What you're going to want to do as a machine builder, when you turn this thing over to your customer, you are definitely going to want to add some password protection because you don't want anybody just going in and modifying your safety program, because then you would have to redo your safety acceptance test. Couple of fail-safe modules here. I've got a fail-safe input module. And this is an 8/16 point module. So you get 8 dual channel inputs, 16 single channel, and then I have a 4-channel output module. Let's look at some of the properties that you can set inside one of these safety IO modules. Under this F parameters, the F destination address. This is a unique identifier that's required on every element of a ProfiSafe system to identify it as a unique device to the safety PLC. So this is set as part of the download process. The same address is set in the output module. So let's jump back to the input. When I'm configuring the specific channels of an input device in the Siemens world, at least, you can actually tell that input module what type of device you're going to be programming. So in this case, I have a 1 out of 2, which is a dual channel device. So 2 signals give me 1 input. 1 out of 1 is a single channel. You can then tell it whether it's a 2-channel equivalent, so 2 normally closed, or whether it's a 1 normally open, 1 normally closed, and how it's wired. So this is a non-equivalent sensor. For this particular input, we've got a hardwired e-stop wired to it. The discrepancy time is the amount of time that that input module gives both of those channels to become harmonized. So either both normally closed or both 1 normally open, 1 normally closed. If it doesn't meet that criteria, it will then generate a safety related fault. And then finally, for this, there's other properties here, but this sensor supply here, I can determine whether I'm powering that signal via the internal supply of the module, which is what you're going to want to do for hardwired contacts. Or I can also choose to power it externally, which you might want to do in the case of like an OSSD input from a light curtain or something of that nature. All of the inputs are paired here because if I'm using them as a single channel, I have both channel 0 and 8 I can use. If I'm using it as a dual channel, then it's just getting reported back as channel 0. There are far fewer parameters for output channels, but there are a couple, so I'll explain those. We are using channel 1 here, so you can activate and deactivate. You can also activate and deactivate input channels. Really, the parameters here are going to be this readback time and the switch on test. This has to do with the testing that the PLC does on the device itself to make sure that it can turn it off and on. This just tells you how long that test will last. And I'm just going to keep the defaults here. At this point, what we want to do is we want to add our Fortress Interlocks device. And whenever you're adding a device from a third party into a Siemens system, you can do that by installing something called a GSD file or a GSDML file. And you can do that by selecting this here. I'm not going to run through that process because I already have it installed. What it's going to do is it's going to put it inside of a folder and other field devices. We know we're doing Profinet, and we have a Fortress Interlock device here, AMGuard Pro. So what I have is this device, and there's two different files here, one that has an RFID solution on it and one that doesn't. I'm going to add the one that has it, obviously, and then I know I'm using this version. So let's drop this here. So there's a couple things you need to do after you drop this into our network. The first thing is to actually assign it to a PLC. So if I click on this little hyperlink here, I can now assign this to this PLC. What it does is it creates a Profinet network, and it also associates this device with the PLC. The other thing I need to do is set the device name. So the device name of this is going to be some type of unique identifier on the Profinet network. And this is a gate. So we're going to identify this as a ProNet gate. Again, you can change this for different gates in the system. If I double click on a device here, it's going to open up the device view. And in the device view, I can then tell this device what it has in it. So I can purchase these Fortress Interlocks devices with safety in it or without safety. And this is kind of how you tell the PLC what's there. So the first thing I want to do is I want to add a safety module. I know I have safety. The safety module is going to add up to 3 fail-safe devices to the PLC, one of them being an e-stop, the other being an auxiliary safety unit, and the other is the safety channel for the head. I have unsafe IO as well that I can add, so let's drop that in here. And that's going to categorize this into a couple different categories. We got lamps, switches, the solenoid drive, and some monitors. And then we've also got our RFID data coming in. So we're going to bring that all into the PLC. What we want to do at this point is we want to tell the PLC and give it names for all this IO. And there's a couple ways you can do that. You can import those names in. I can type them all in individually. I think personally the best way to do it when you have some type of a bit configuration here or data map is to come up with your own data structure on how to implement the IO. So I'm going to do that. You guys don't want to see me type all this stuff in. So I'm just going to bring it in from a library. So let me grab these data structures, something called the PLC data type. And what this does is telling the PLC what the bitmap is for all this IO that's coming in. So let's just take a look at one of these. Our safety inputs, we've got the e-stop channels, we've got the auxiliary channels, we've got the head channels. We also have something called a QS. This is a quality service bit. This just basically tells us that our inputs are valid. If I look at my standard outputs, for instance, I've got my access granted and denied. You could bring this in as a generic thing and customize it for each one of your inputs as well. From here, what I want to do is I want to take these data structures and assign it to my IO. And I can do that in a PLC tag table. And again, you guys don't want to see me type all this stuff in. So I'm going to bring in a predefined tag table. And then I'll show you what it's going to look like. So I have a Fortress AMGuard device here. This is going to be my inputs and outputs and my safety. When I expand this, this is the bit pattern for all the stuff that I have here. So let me just show you how to add that on this gate safety out. So let's type in my tag name. Safety out. What I need to do here is choose the PLC data type. So I'm going to choose my safety outputs. And then I need to give it the first starting address. So I know we start at Q23 for my output. So now I've got the right data structure. All of my bits correspond to my actual bits. So we're good to go here. Let's switch back to the ProNet unit. I talked about before some of the safety parameters. Safety parameters on the ProNet, no different. I have a specific fail-safe data area here. I can give this thing also a fail-safe destination address. And I know this is set to 10. So there are really two methods of assigning a fail-safe destination address. Some devices use a dip switch to set it. Other devices have just a memory chip in it. So you'll assign it with the software and the memory chip holds that safety address. The Fortress unit happens to have dip switches. The Profinet push buttons happen to have a software-based one. So I know that this is set to 10. All right, at this point, let's go ahead and also add my Profinet station for my e-stop. And again, you don't want to see me run through this. So I'm just going to add it from this pre-configured device. So I've got assign it to my PLC. You can also tell this which IP addresses to use. So let's change this guy to like .4 just for fun. And then I'm going to show you a little bit what it looks like here with my Profinet push button. So with my Profinet push button stations, I've got my e-stop, and these are all the buttons to the right of it. And their own IO are associated with this. So let's assign that IO. We're going to do the same thing so you don't watch me type all this stuff in. I'm going to bring in a predefined tag table that has all of my Sirius devices here. So now we should be set as far as configuring the hardware goes. Now let's actually get into actually doing our programming. So from a programming perspective, if I open up the program blocks folder of my PLC, I got a couple of different predefined blocks here. And because I'm using this as a safety PLC, I've got my main safety PLC program. This is where all of my safety code will be initiated from. This is called the main safety runtime group. It's this block here. And then all of my standard code is going to be initiated out of my main routine. So this is this OB1 here. We're going to be doing some programming in both of these. Siemens does recommend when you're doing safety PLC programming to have some type of data exchange area where I can take data or bits or whatever information you want out of the standard program, send it to the safety program, and then vice versa. And what I've done is created a data block to allow me to do that. And again, it's not a difficult process. I just don't want you to have to watch me type in all these variables. So we're bringing it in from a library. This data area is called the data block. We named it Safety Data Exchange. And there's a couple of different categories within it. We've got data that's going to the safety program, which is going to be a reset command. It's going to tell the safety program that our system is started. And it's going to tell our safety program that our shutdown is complete. And what does the shutdown complete mean? It means when I want access into my gate, I'm going to give the saw a chance to fully stop before I allow them to come into the gate area. So that's going to be with this bit. From the safety program is really going to be like e-stop status. It's going to tell me whether or not I should be resetting things so that I can manipulate my non-safe data in order to do that. So let's start out with our safety programming. We open up our function block for safety programming. And the idea with safety is to keep it simple. I mean, this has kind of evolved from a control relay to a safety relay into a safety PLC. So the idea here, you got to keep things simple. So there are limitations on the type of blocks that you can put into a safety program and the type of instructions. You pretty much have your simple bit logics. You've got some timers and counters, but that's kind of it. There's also some TUV certified safety blocks. These are what you're going to use quite often to evaluate e-stops. We've got things to evaluate two-hand stations. I can do some muting as well. I can do a feedback monitoring. That's what we're going to use for our safety contactors for our conveyor, and then safety door monitoring as well. The other block here is this global acknowledgement block. We're always recommending putting the global acknowledgement block into a safety program. What that does is it resets safety related communication errors in the system. And we want to use this safety data exchange and reset input in order to actually do a global acknowledge on my safety devices. The next thing that we're going to add here is some code in order to make sure that our Fortress Interlocks units are giving us valid signals. And for every input channel in a Fortress Interlocks safety unit, there's also an output that allows you to reset that in case of a fault. So we are going to use the same reset button here. And then in here, we're going to assign this to a safety output on our gate. And it's to reset the e-stop channel 1. And let's do the same thing for our e-stop channel 2. And then we're also going to do that for our head unit. So let's assign those. We're not using the auxiliary channel on this particular device, so we don't need to worry about doing that. So these two networks here are just kind of safety reset stuff. So something happens on the safety side of things, we can then reset that fault. The next series of blocks we're going to put in our e-stop evaluations. So if I grab this emergency stop block, and we bring it in here, this first one is my AM guard 8 e-stop evaluation. So I'm going to do that here. There are 2 input channels coming from the Fortress unit, one for channel 1, which is my safety input e-stop, and then the other is for my channel 2. So let's go ahead and add this. This particular block is both a stop category 0 and a stop category 1 block. So stop category 0, it's going to drop this output as soon as the input drops. Stop category 1 is going to be a delayed stop. In order to reset this thing, we're going to reset it here. You can add this time delay for the delayed stop. I'm going to use the same block to evaluate my head unit. So guard gate head. And again, we got a couple of inputs here. This is our gate safety in on our head. This is our gate safety in channel 1. Whoops. I transposed them. Sorry about that. And now we're also going to evaluate our Profinet push button e-stop. So this is simulating our panel e-stop. So we'll just feed that in here. Our panel e-stop. This was one of the tags we brought in the tag table. And then what we want to do is pull the e-stops together because they're performing a specific safety function. So our AM guard e-stop, as long as that is good, and our panel e-stop, as long as that is good, we're going to turn on this bit that says e-stops. Okay. Now this is a tag that we haven't created yet, so let's define it as a static variable in my safety block. Find that here. Let's move on from here and actually put in the code to turn on our saw. So we're going to be using a couple of bits from the standard program to initiate this, as well as evaluating some e-stop data. So the first thing is going to be our safety data exchange to telling us our system is started. And this is also our shutdown here. We're going to be using our e-stops okay here. So if we drop an e-stop, we're going to drop its saw. And then we also want to use our head unit to make sure that if the head is removed, we're going to turn off the saw. So let's run the saw here. So that's our simple code to turn our saw on and off. Let's use the feedback block for our safety contactors on the conveyors. So these are our safety contactors. And to turn these things on, we're going to use the same system started bit we used up here. And then we want to make sure that the e-stops, if they happen, they shut this thing off. So a couple of other things we have to feed into this block. First is the actual feedback from the devices. And these are directly from the contactors. They're coming back into a standard input. Does not have to be a safety input. And again, these are certified blocks. And then the other is something called a value status. For each output in a Siemens safety system, there is also a value status associated with it. That is very similar to the quality status bit on the Fortress units. What this block needs to know is that if I'm going to be turning on an output, I need to make sure that it is a valid output. So we feed these in here, our value status. And then we want to do our reset as well. That's going to reset the block because we want to manually reset it. And again, whenever you see this acknowledgement necessary input, if I feed it true into here, I have to initiate a reset manually. If I feed a false into this, it means that it's going to auto reset. So I can kind of show you that on this amp. Let's say we want to auto reset this. We may or may not want to actually do it, but I'm just going to show you that it's available. And then finally on our feedback block, we want to feed in the time that the block is going to give the output and the contactor feedback to align themselves. Once we have the safety contactors feedback block done, we're going to use the output of that to actually turn on our safety contactors. So safety contactors output. This is going to be our conveyor contactors. So we use 2 of them here. So this is kind of our safety code. This is what we're going to use to turn our stuff on and off from a safety perspective. The other thing that we have to do is configure some of those bits to send data from the safety program to the standard program. And what I'm going to do is actually utilize this safety data exchange block. And there's just some information in here that's being sent from the safety program to the standard program. Again, you don't want to see me type all this stuff in. So that's going to be our safety code. Let's write some code in the standard program to do this. Just like with many things here, we're a little bit limited on time. So there's a couple of predefined blocks that I'm going to pull in here. The first block I've written is an access control block. What this is going to do is for every access control station we have in the system, we're going to feed in the IO necessary to control that. The other thing we're going to feed in is a system block. And what the system block does is starts and stops the system. And it also tells the lights to turn on. So again, you don't want to see me type all this stuff in. But what I will do is feed in the standard IO that's on the Fortress unit for my access control. So we've got our gate in. This is our start button. We've got our gate in. This is our reset button. We've got our gate in. This is our head monitor. We've got to feed in our RFID data because we're going to be evaluating that to determine if you have authorized access. So this is telling the safety system that the shutdown is complete. This is telling the light to turn on if you have access that's granted. This is telling the light to turn on if you have access denied. This is actually controlling the gate solenoid. And finally, we've got a reset ready bit that we're going to turn on here. So at this point, we're ready to roll. We're going to download this into the PLC. Let me just switch back to our station just to give you a real quick recap of what we're downloading to. So let me stop sharing that screen. George, can you see my screen again?
Yep, we sure can.
Okay. So again, we've got our PLC, Profinet push button station. We've got our Fortress station. The way this is going to work, start push button, stop push button, start push button here, and e-stops. So let's download this. Let me share my screen one more time. So I'll show you the download process. Okay. So we're going to take the PLC code we just wrote. Whoops. Let's make sure that we're downloading to a fresh system. So let me cancel this out and we're going to go download and reset. This is going to wipe what's in the PLC out right now and load our stuff. Okay, loading might take a second here. What this is doing is deleting the stuff that's in the PLC now. It's going to go ahead and load the configuration that we just created. Once it's loaded, we're going to start the module. And then we are going to test. So let's switch back to my station. Okay, what you're going to see right now, we've got a reset light flashing. Anytime a safety system comes up and you're manually resetting an e-stop, it's going to have you do this right away. So that's something that you're going to have to do. This is resetting our e-stop blocks. No big deal. So if I hit my start button, my conveyor contactors pull in, my light turns on. I can stop it here, start it back up. I've got my panel e-stop. It's killing both. Once I release that button, I can reset it here, start it back up. On my Fortress unit, I hit the e-stop, same thing. I can reset the e-stop, start the system back up, so I'm up and running. So at this point now, we got a couple of operators here. They want to be able to access the system. So let's tell them whether or not they can do it. So first of all, we got Matt Cooper. And Matt Cooper's got his own employee badge. He's kind of a slouch. I wouldn't trust him inside of the machine, personally. So let's wave his badge here. We're going to deny him access. So our access denied light comes on. So Matt's not happy. He calls up his buddy George, who is only slightly more reliable than Matt is. So now George is going to want to get in. Nope, we've got access denied. So, and again, you cannot, it's not allowing us to open this door. Finally, James Thomas, who actually is a good employee, he's going to come to the rescue. He's actually authorized to get into this gate. So let's swipe his badge. We're going to give the saw a chance to power all the way down. After a few seconds, the saw is off. Access is granted. The system is still partially running because we have our conveyor running, but you remember, we designed out the pinch points and the dangers of the conveyor system. And we've actually energized our solenoid. So now I can go ahead and open my gate. James is going to do his thing, whether he's cleaning the machine or replacing a saw blade, something of that nature. He's going to shut the gate. He's going to go ahead. Once the gate is shut, at that point, I can hit the reset button. What that's going to do is de-energize the solenoid. So I no longer have access. And then I'm going to go ahead and start it back up. So my saw is running. Everything is safe. So from a live demo perspective, I think that pretty well covers things. What I want to do now is switch back to the main PowerPoint. And let me share my screen. My back. Okay. Let's kind of wrap this up then. I mean, we've showed our live demo. We went through our risk assessment. We've implemented the safety reduction measures. Let's talk about some additional resources here. The first thing we want to talk about, if you're interested in actually learning more about risk assessments, there actually is a certification process that you can run through. We've got 3 folks at Electro-Matic that have actually run through this certification process. Myself has done it. George has done it. Sarah Groden, who is our robot units product manager, she's actually run through this as well. What this is a series of 5 online modules that basically steps you through the ANSI B11 standard. At the end of those modules, there is a test you can take directly from ANSI V11. If you pass the test, I believe it's a 50-question test over 90 minutes, open book, open note. But as long as you learn everything correctly inside of the modules, you take the test, pass the test, and you're also can be a licensed machinery safety specialist. So if you're interested in that, definitely get with us through Electro-Matic. We can get you signed up for that. Fortress Interlocks actually teaches this workshop. It's really, really good. Actually, there's a couple of folks at Fortress, Eve and Malcolm, that are very, very knowledgeable when it comes to safety and safety standards. As a matter of fact, they sit on a couple of safety boards. They run through this information. They make it fun. They make it interesting. If it's something that your company needs to have a licensed machinery specialist, this is really something that you're going to want to take. It's really, really good. But yeah, with that, we do appreciate everybody's time. We realize how busy everybody's schedules are. Really hope you learned something from this. My contact info, George's email as well is on here. If you have any questions, please feel free to reach out to us. But with that, we will sign off. Have a great day.
Thanks, everyone.